And this is the Stanford Math Tournament Number Theory problem number 3. Here's a view of this problem. Suppose that a positive integer n has 6 positive divisors, where the third smallest is a and the eighth smallest is n over 3. Find the sum of all possible values of n. Alright, so first thing I want to notice is that when it says n has 6 positive divisors, we can immediately conclude a form for n. N is either of the form p to the phi, or it can be of the form pq squared, where p and q are primes, right? And these are the only forms possible because 6 can only be decomposed into two products of two prime numbers. Alright, so now let's move on to the rest of the problem, where the third smallest is a and the eighth smallest is n over 3. So we only have 6 possible values of a. Let's try to maybe go through them all. If a is equal to 1, we have the third smallest is a, and the eighth smallest, which is the first smallest, is n over 3. So if the third smallest is a, which is 1, and divisors are all positive, it really doesn't make much sense, right? Because you can't have a divisor that's less than 1. So a does not equal 1, that's already out of the question. How about 2? If 2, then the third smallest is 2, and the second smallest is n over 3. Again, that doesn't make too much sense, right? Because how can anything, the only smaller divisor than 2 is 1, and that happened when n equals 3, and n equals 3 is not of this form. It doesn't have 6 divisors, so a does not equal 2. How about 3? Well, 3, then we had third smallest is a, the third smallest is 3, and the third smallest is n over 3. So that only occurs if and only if n is 9, and 9 is of the form p squared, which is none of these. So a does not equal 3 also. Alright, now let's move on to a equals 4. The third smallest is 4, and the fourth smallest is n over 3. So maybe that's possible. So if a equals 4, we have the third smallest is 4. I'm going to write this as 2 squared. So if our numbers of the form p to the 5th, since we have a 2 squared factor, we know that n must be of the form 2 to the 5th. From which, let's see if this checks out. We have the third smallest is a, which is 2 squared. That indeed is the third smallest. We have 1, 2, 2 squared. And then we have the 8th, which is the fourth. The fourth smallest is n over 3. Well, 2 to the 5th is not even divisible by 3, right? Because it only contains one prime. A prime to a power, which is not 3. So this is not divisible by 3. So this doesn't work for this case. If it's of the form pq squared, then well, q squared is already occupied by this 2 squared from a, right? So p, and we also know that n over 3. So we also know that there's a divisor n over 3, meaning that our number has to be divisible by 3. Therefore, n must be of the form 3 times 2 squared in order for this to work. So now let's see if this checks out. Third smallest is a. So the third smallest would be 1, 2, 3. Third smallest divisor is 3, so this does not check out since we have a equals 4. How about now a equals 5? A equals 5, let's see, third smallest is 5 and the fifth smallest is n over 3. Again, if it's the form p to the 5th, then it must be 5 to the 5th, right? But 5 to the 5th is never divisible by 3, so we don't even have to worry about the p to the 5th case. So now let's just worry about pq squared, where the third smallest is 5 and the fifth smallest is n over 3. So we know that we must have a factor of 3. So let's first say that p is equal to 3. So we have 3, and we know we must have a factor of 5. So we have 3 times 5 squared as an option, which is equal to 75. Let's see if this works. The third smallest is 5. That's indeed true because we have 1, 3, and then 5. And then the fifth smallest is n over 3, which is 25. So the second to largest is 25, which is indeed true because it goes 75 and then 25. So this number satisfies. And now let's not forget our other case of pq squared, where we're not taking q as 5, we're taking p as 5. We're taking p as 5, and then we're taking q as the 3, so 5 times 3 squared. This gives us 45. Again, checking if this works. The third smallest divisor must be 5, we have 135 that checks out, and then the fifth smallest divisor is n over 3, which is 15, which goes 45, 15, so this is true as well. So now the only other case to check is a equals 6, which automatically doesn't work by basic logic because the third smallest is 6, and the sixth smallest, which is the last divisor, which is the biggest divisor, is n over 3. But we know that n is the biggest divisor, not n over 3, so this case doesn't work. So we have found our two numbers, and we can sum them to get 120. And we are done.